Since you have no class, no more class except my classes, so I can take that class.
Okay.
Okay, chapter 8, root locus. We will start the chapter 8, which is the root locus. Root locus techniques. Okay, so root locus technique we will start today. So first of all, what is the root locus technique? See, root locus is a graphical representation of the closed loop poles as a system parameter is varied, and is a powerful method of analysis and design for stability and transient response. মানে এটা হচ্ছে একটা graphical it is a graphical representation, right? It is a graphical representation. That means you show the root locus through the some graphs. Okay, and it is a method of analysis and design for stability and transient response. Okay, it is a powerful method of analysis and design for stability and transient response. Okay, so the root locus can be used to describe qualitatively the performance of a system as various parameters are changed. For example, the effect of varying gain on percentage overshoot, setting time, and peak time can be vividly displayed. Besides transient response, the root locus also gives a graphic representation of a system stability. So we see this one by one. Okay, so by using the root locus, you can give the graphical representation of the system stability, and you can also analyze the transient response. So that would be nice. So if you understand it, let's see. Designing the root locus, it can be defined as the representation of the word paths of the closed loop poles as the gain is varied. It can be defined as the representation of the paths of the closed loop poles as the gain is varied. So if you change the gain, then it would be changed. Let's say. So just look at this one. K over s square plus 10s plus k. Here we'll change will vary the value of k. Okay. If we change the value of k, then we'll get some values of poles. So if we put the value 0 here, if k is 0, then pole would be -10 and 0. Two pole would be there. You understand how it comes. If k is s square plus 10s, since k is equal to 0, so you can write it as if you take the form. Let's say so you can do what? So make the value, take the value. So it would be -10 and 0, two value. It is clear. And if you put the value is s square plus 10s plus 5, s square plus 10s plus 5. Then you can take the values. Okay, just do the calculation, below down factor, then you get it. Okay. So these are the values. Okay, now that is the way you can find the different types of poles. Okay, so that means k is the gain. So if you are changing the values of k, then you are getting different types of poles here. Okay, that is the thing. So that is the explain. So here we put the poles here. You see, the root locus shows the changes in the transient response as the gain k varies. So if we vary the gain k, then the response, transient response will be changes. First of all, the poles are real for gains than less than 2s. Thus the system is overdamped. At k is equal to 25, see, when k is equal to 25, poles are real, but when the k is equal to 30, it becomes imaginary. Poles are real and the multiple and hence critically damped. As at k is greater than 25, the system is underdamped because it becomes imaginary. So overdamped, underdamped, these things we have studied earlier. So from understanding underdamped portion of the root locus, k is greater than where k is greater than 25, we see that regardless of the value of gain, the real parts of the complex poles are always the same. So settling time remains the same regardless of the value of gain. Since k is equal to 4 by 60. Yes. Okay. So if k is increased, the damping ratio diminishes and the percentage overshoot increases. The damped frequency of oscillation, which is equal to the imaginary part of the pole, also increases, resulting in a reduction in peak time. Finally, since root locus never crosses over into the right half plane, the system is always stable regardless of the value of the gain and can never break into oscillation. Now see, what are the properties of the root locus? That is important. Because we need to know this to understand the problems here. To understand the upcoming problems, we have to look at here. Okay. Let's see, what is the properties of the root locus? The sum of guys are trying to join. Okay. Let's see. So now look at this equation. Kgs divided by 1 plus Kgs into Hs. Okay, this is the transfer function. Now here, let 1 plus Kgs into Hs is equal to 0. Then Kgs into Hs is equal to minus 1. Okay. So from here we get the two property. Kg, the Kg modulus of Kgs and Hs would be 1. And the angle of Kgs Hs is equal to 2k plus 1 into 180 degree. Where k is equal to 0, plus minus 1, plus minus 2, plus minus 3, blah, blah, blah. And here we can write the k is equal to what? 1 over Gs Hs. Remember, from these two equations, we'll do some maths in the coming things. In the coming, after a few moments. So that is your general equation. By following this equation, we'll solve the upcoming maths. Okay. Now see the rules of sketching the root locus. How you would sketch the root locus. So see, few things are there, like number of branches. The number of branches of the root locus equals the number of closed loop poles. First condition, the number of branches of the root locus equals the number of closed loop poles. So number of poles would be equal to the number of branches here. Symmetry, the root locus is symmetrical about the real axis, so it would be symmetrical. So the root locus would be symmetrical about the real axis. The root locus is symmetrical about the real axis. So first point is number of branches, second point is symmetry, third point is the real axis segments. Real axis segment. On the real axis, for k is greater than 0, the root locus exists to the left of an odd number of real axes, finite open loop poles and infinite open loop zeros. Okay, for k is greater than 0, the root locus exists to the left of the odd number of real axes. Left. Okay. When k is greater than 0, then the root locus exists to the left of an odd, to the left on the odd number of real axes, finite open loop poles and or infinite open loop zeros. Okay. Starting and ending points. Starting and ending points. The root locus begins at the finite and infinite poles of GSHS and ends at the finite and infinite zeros of GSHS. The starting and ending point, the root locus begins at the finite and infinite poles of GSHS and ends at the finite and infinite zeros of GSHS. It starts from the pole and it ends at the zeros. Root locus starts from the pole and it ends at the zeros. Behavior of the at infinity. The root locus approaches straight lines as asymptotes as the locus approaches infinity. Further, the equation of the asymptotes is given by the real axis intercept, sigma a and angle theta as follows. So sigma a, that is the equation. What is the sigma a? Sigma is equal to summation of finite poles minus summation of finite zeros. The difference, and number of finite poles minus number of finite zeros. And theta a 2k plus 1 pi divided by number of finite poles minus number of finite zeros, where the values of k are 0, plus minus 1, plus minus 2. Okay, so real axis breakaway and breaking points. And another point, the point where the locus leaves the real axis is called the breakaway point, and the point where the locus returns to the real axis is called the break-in point. 2 points are there. One is breakaway and one is break-in. So if we consider something like that and say that is the pole, these are the poles. I do not know what happened to my mouse. These are the zeros. So this is the breakaway. That is the breakaway point. This one is the breaking point. So that is breakaway. That means from where the root locus leaves, and breaking where the root locus leaves. Break away and breaking points. These 2 points are there. Okay. So breakaway points and breaking points via differentiation. Here see uh, k. Let's take a look the equation k into s minus 3 into s minus 5 divided by s plus 1 into s plus 2. Okay. Now you do the calculation k into s square minus 8s plus 2 divided by s square plus 2 plus 2. Okay. And here for here we can see that for all points along the root locus, k is equal to minus 1 and s is equal to sigma. So we are taking what? We are considering k gs into h is equal to minus 1 and s is equal to sigma. That means this thing is equal to minus 1. And instead of s, we are writing the sigma. So we put this one is equal to minus 1. Now determine the value of k. Differentiate with respect to the sigma and derivative. We are setting the derivative as 0. Okay. Now solving for sigma, so we found that sigma is equal to minus 1.45 and 3.8. So if you do the calculation, and which are the breakaway and breaking points. So with the differentiation, how you also see one point is 3.82. So 3.82 is the breakaway point and minus 1 point something, that is the breaking point. Okay. Like this way we can calculate. So you see here it's simple. You can, if you put the value of minus 2, then you will get the pole, and if you put the minus 1, then you will get the pole. And if you put the 3, then it will be 0, and if you put the 5, then it will be your pole. These are the zeros. That's 5 actually, not 4. That is 5. Okay. Now, without differentiation, we can also solve this one. Breakaway and breaking points without differentiation. Breakaway and breaking points. Now see. So you have to satisfy this equation. Summation from 1 to m, 1 divided by sigma plus zi, due to summation of 1 to m, 1 divided by sigma plus pi. Where zi and pi are the negative of the zeros and pole values. These are the negative of zeros and pole values. So 1 over sigma minus 3. See, so what are the zeros values? 3 and 5, right? Zeros values are 3 and 5. And what are the pole values? Minus 2, minus 1. That means plus 2, plus 1. It will be plus 2. Now, if you do the simplification, then you will find that this equation. Sigma is equal to 1 minus 1.45 and 3.8. The same equation will come. Same values will come. So that's how, that is the way to determine the breakaway and breaking point. Okay. Now see, j omega axis crossing. That is another one. See, this is a closed loop equation. Now, closed loop transfer function is given. From here, you have to determine the some values. Just first of all, you do the Routh-Hurwitz table. Okay, Routh-Hurwitz criteria. 1, 14, 3. 1, 14, 3k. 7, 8 plus k, 0. Now do as usual simplification, then you find this. Now here, let's say this complete flow will be zeros. The complete flow of zeros yields possibility for imaginary extreme. So if this one is equal to 0, then all zeros will be possible. So you do the math solution, then you get it. is equal to 9.65. So forming for C, so if you put the value of k is equal to 9.65, then this row will be 0. So you have to consider this one to determine the polynomial. So s square and k is equal to 9.65 even polynomial. So now you get the value of k is equal to plus minus 1.5. So the root Lucas crosses the j omega axis at plus minus 1.59 at a gain of 9.65. So the range of k is this one. So that is how solve this problem, this kind of problem, j omega axis crossing. So if you want to find out the j omega axis crossing, then you have to proceed like this. Okay, so you have to proceed like this. That is the final one, final example. Skill assessment exercise 8.4. Now, see the question here. Given a unity feedback system that has the forward transfer function, so it is a transfer function. Now you have to calculate these things. Sketch the root Lucas. Find the imaginary axis crossing. Find the gain k at the geometry axis crossing. Find the breaking point and breakout point. Find the angle of departure from the complex plane. So last thing we have not discussed yet. So first of all, sketch the root Lucas. So to determine the root Lucas, what you have to do. So see 0 at s is equal to minus 2. 0 is equal to minus 2. For poles, you have to calculate this. So consider it as 0, and we can use this formula. Put the values here, values of EAC. Then you get the 2 plus minus 3i. So how to write this poles? 2 plus 3i, 2 3i. Here 2 minus 3i, 2 minus 3i. And another one is equal to minus 2, is equal to minus 2. 0 is here. Okay, is equal to minus 2. Now you have to consider this one. That is how you have to write the Lucas, scale the Lucas. Second one, second question, find the imaginary axis crossing. So for the imaginary axis crossing, consider this one. We know that GS plus 1, GS divided by 1 plus Hs. So the values are given here from the equation. K into GS is equal to K into S plus 2 and 1 plus GS. These things is equal to this one. Now do the calculation here. And then finally get is value of S and C and the gain K at the geometry. So gain K is equal to 4. K is equal to 4. If you put the 4, then it will be 0. And D. Find the breaking points. K GS into H is equal to minus 1. K into GS. So what is the value of GS? That is the GS divided by HS. GS by HS. This thing. It's equal to minus 1. Instead of S, you take the value sigma and do the calculation, then differentiate. Finally, you get the values here. The last part, this one, zero angle from the pole. And this thing, I think I'll have to discuss in the next class. Okay. This part will be discussed in the next class, inshallah. Only this part left. All other parts have been completed.